So what even are the gas laws? And why are they so important?
To answer such question, we must first look at Boyle's law, which states that the relationship between pressure and volume is inverse. That means when one increases, the other decreases and vice versa. Lowering the volume means particles will travel a shorter path to the distance of their container, therefore creating more pressure. That is why when there is less volume, there is more pressure. The images below show a perfect example of this. The first image has less pressure since volume is greater, and the second one has more pressure because volume is lower and the particles more condensed together. By running a simulation, which can be seen in the images at the left, we were able to translate this law into an example of how it will work. In the graph at the right, we see that as the volume increased, the pressure decreased and the yellow line, or the constant, remained horizontal. We should note that the constant is the product of pressure times volume. Yeah. So, Enrique?
Of course. So now we go on with Avogadro's law. Avogadro's law asserts that the relationship between volume and the number of moles is proportional. This implies that there is a ratio between the number of moles and the volume, meaning that when the amount of particles inside a container increases, to keep the pressure the same, the volume must increase. The opposite would happen if the amount of particles decrease. This is shown in these two images. In the first, we clearly see that because of the small space, the particles are more close together, they're huddled up. And in the second, the volume is larger, which means they have more space to go around and they're more separate. So over here, we have Avogadro's law proof calculations. So here we have the chart that contains, well, the data that we obtained. The yellow line represents the volume, the blue line represents the number of moles, and the red line represents the constant, which is also the dividend of the volume by the number of moles. Avogadro's law can also be shown in, well, a balloon practically. For example, if you were to blow air into a balloon, you would be practically adding more moles to the balloon, which would make it so that the balloon expands. That is the reason why a balloon expands when you add air to it.
And that is what is shown in the graph. Next up, we have Guy-Lussac's law, which asserts that the relationship between pressure and temperature is proportional. That means when pressure increases, so does temperature. When pressure decreases, so does temperature, assuming always that volume is constant. This also means they have a pattern of proportionality. We can see this in the images below. The blue one has lower temperature, therefore having slower particles, which means less pressure. The one at the right has a higher temperature, therefore faster moving particles and greater pressure. So again, we ran a simulation and the Guy-Lussac's law is present in the graph by how pressure rises with temperature. In any part of the graph where the quotient of pressure divided by temperature could be calculated, its value would always be the same. This means the quotient will be a constant and that this law applies. So Enrique, your turn.
So now we shall move on to Charles's law. Charles's law has to do with the relationship between volume, temperature, and pressure. If the temperature increases, the pressure increases. When the temperature decreases, the pressure decreases. That means that when heated, particles move faster, colliding more frequently, and therefore creating more pressure. And when cold, gas particles move slower, therefore taking up less volume. Like we see in the image, which is a graphical representation of the results following a gas reaction including the same principle. How when pressure is constant, volume increases with the temperature in the graph. So over here we have the Charles's law, proof calculations. So here, temperature is measured in Kelvin and volume in nanometers. Increasing the temperature while pressure is constant, as can be seen in the bottom left, causes the volume to increase and the box expands. The units shown this are on the table in the top left corner. The graph visualizes the information. As the temperature, I'm so sorry. So as the temperature, which is the blue line, increases, so does the volume, which is the red line, and the constant, of course, stays the same.
So lastly, we have the ideal gas law, which is the conjunction of all the gas laws together. This law only applies to ideal gases, meaning when none of the gas particles interact with or attract each other. In the graph at the side, we can see the interpretation of most gas laws. Guy-Lussac's involving pressure and temperature, Charles's involving volume and temperature, Boyle's involving pressure and volume. Though Avogadro is not represented in the graph, it would involve the number of moles plus the volume. We also tried making a graph to represent the ideal gas law through our simulation. And in the graph, the rise in volume caused by the pressure and the number of moles, The rise in volume causes the pressure and the number of moles to drop, since there is less concentration of particles, meaning these spread out more. So it just connects all the dots together. For those who want to experiment individually with each principle, you have your list of experiments you can do. You can pause the video and see them for yourself. Next up, Enrique.
Practically, now we know how the gas laws work. So how can we simulate them?
We should first see to the theory. And let's start by, what do cars, planes, and ships all have in common? Well, the answer is they are all propelled through what's called an internal combustion engine. Moreover, these are motors that use gas to create a force inside the motor that moves the object and accelerates it. The process through which this happens is called the Otto cycle, and is caused by a sequence of gaseous interactions that can be explained through the ideal gas law. The image at the left explains this very clearly. So, from the first to second phase, the piston in the engine supposedly fires back, opening the initial valve and hauling in the oxygen and gasoline mix. From the second to third phase, the piston compresses and increases the gas temperature, which, along with the ignition that creates a spark, combusts the oxygen and gasoline mix. From the third to fourth phase, the explosion pushes the piston back, letting out the compressed gas. And from fourth to first phase again, the piston recoil sucks oxygen and gasoline once more, continuing the cycle. To explain why these reactions happen, we should look at how the gas laws can explain them. So the first phase can be explained through Avogadro's law, which says that because the number of moles inside the motor was too little, then of course the piston must fire back like it would do in the Otto cycle. Secondly, the piston compression happens according to Gay-Lussac's law because of pressure. Escalation in pressure set off the rising temperature. And in the third phase, the explosion pushed the piston. This relates to Boyle's law because the pressure created by the explosion inside sought to equalize itself, and this let out the compressed gas. And the fourth to first phase again, when the things repeat again, the piston recoil sucks oxygen in the gasoline once more. This again happens because the number of moles inside the motor was too little, according to Avogadro's law. And Enrique?
Now we go on to practicality. Here are the ICE components. So first we have the crankshaft, which consists of a series of cranks and crank pins, which the correct rods of the engine are attached. We also have the rocker arm, which opens and closes the exhaust and intake valves. We have the belt wheels, which spins around the timing belt, making it move. We have the air filters. They clear the air intake from debris and plug it up. The oil pan, which is a hollow object for the engine oil. Piston, they, along with the igniter in the compartment, pistons compress the air and set off the combustion phase in the engine. The engine block. It makes it so the pistons can move inside the cylinders, which moves the crankshaft and therefore moving the wheels. And the engine valve. They allow the air into the cylinders, which help the fuel and which helps ignite the fuel and move the piston. So here we have practically how we made the engine model. It is virtually modeled and represented here following Da Vinci's technical drawings. Numbers near the pieces are with the definitions inside 18. The animation also shows the final product, how it would look like, made in real so accurately resemble the real engines we use in cars.
So, after understanding the physics of gases and how common engines work, you will never have to be stuck on the road again because of a busted car engine. Next time you have a problem with your auto, you'll hopefully be able to find your way around. These are the credits. And thank you so much for your time. This was our science fair.
Yes, I hope you have a great time.